Okay, so thank you very much, Gianmarco and the rest of the organizers for fitting me in just to show some of the sort of data infrastructure I've been using recently. Many of you know I was previously in Nicola Martari's group working on AIDA extensively. So I arrived at DTU in October. For those of you that don't know, so I'm in the energy section, and there's, let's say, our sister section, if you like, that can be the physics section, who are responsible for the ASE library, amongst many other contributors, of course. So ASE is very heavily used over there. So we use and implemented AIDA on our systems, and we're doing high throughput studies using that as well. But it was clear that for a lot of people, it was just too big a barrier to overcome, and they were really comfortable with the current set of ASE tools. So I've tried to come up with a system where we can use the two together and, in effect, also simultaneously solve some of the other, let's say, problems and issues that I have regarding the way that we use data for these big data projects, and also for my project in particular, which involves a lot of machine learning. So I often need to pull up large data sets, operate on them, and then put them back in storage, and so on and so forth. So I'll just show you some of the tool set that we use, including a short demo. But first, let me just go in a little bit more detail into the sort of motivation behind this. So what I was seeing, I guess to a lesser extent back in Lausanne, but especially here at DTU, is, people have their data silos, and this is really, I would say sort of active data, the stuff that they're working on at the moment, rather than polished stuff. And there's a lot of sharing of this, but it's really super ad hoc and, in my opinion, not very nice. So people send around tarballs, exports of snapshots of their database, even worse, maybe binary objects, pickles, data frames, and so on, or they just send me a path, on the supercomputer saying, okay, go there, get what you want, and then I copy it locally and go from there. And really, it's not a very nice way to collaborate, especially because then when we want to re-merge our data back, or they then want to work on something that I've been working on, it's really, in my opinion, a mess. And I think we can do a lot better than this. And in a way, the examples I was thinking of in my mind is, well, we've got all sorts of great examples out there. GitHub obviously works perfectly for the development of software. There's a lot of ideas we can bring in from there. Google Docs, Overleaf, things like this. And what I really wanted was a tool where I could work interactively with others at the same time on the same data, but in a way that didn't impose too many changes to the way that people already work, because I can see there's going to be a great resistance to that. So the wish list, in a way, I often start my talks like this. What do I really want? What's the goal I want to achieve from this tool? Well, as I said, real-time collaborative working, if possible. I want it to, so I'm working in Python. That's kind of a given. Most people are happy with that. I don't really like Python, but that's the way it is. So I work with it, and I want Python objects to be able to be compatible with this database without modifying them, right? So an ASC atoms object, I can't change that code. It either needs to work, or I can't use that object directly. Of course, I can always transform it, but that kind of moves away from the spirit of what I'm trying to get at. I want to be able to reorganize my data, right? So one of the nice things about having a directory structure is you realize, oh, actually, I want to study another compound. Well, you just group everything you had into the name of the compound you studied, add another folder, and carry on from there. It's really minimal effort to adapt and change what you've already done to continue your project on. If you imagine if you have a very rigid database structure, that's very difficult. Discoverability, so I want to know very, very quickly what's in someone else's database, roughly what's the lay of the land, what have they done, what are their results, and so on. A big focus on obviously big data. I mean, that's why we're all here, but I guess I'm getting at a different end of this, which is I want to be able to stream, gigabytes of data into my machine learning model to my GPU and then back out. So I need to be able to query for the stuff that I need very quickly, bring it across, and then push it back to the database. Okay, so what I've come up with is a library called MincePy. So MincePy is basically kind of like an ORM. It has support for saving effectively any Python object that you can define these 4 methods for. into currently a MongoDB backend, but the sort of backend class is modular. So you need to tell me, how to transform your current instance into some kind of a saved object, into a saved thing that the database can understand. So dictionaries, integers, lists, so on. You need to be able to then recreate yourself from that. And because I use hashes for everything, you need to also be able to tell me how to hash your object and equate it with other objects. But that's effectively it. So, and you can see this isn't an object that the thing you want to save would derive from. It's not going to, there's no inheritance relationship. This is just something that tells me about your object. And then as long as you set this type here, I know, okay, every time I encounter an AC atoms, I need to pull up this guy, and then I can work with the AC atoms. So that's, I think, the only bit of code that I show, because I think it's quite central to what I'm doing. And the features of MinSpy, so this sort of object relational mapper, for those of you that are familiar with those, is it can very quickly and quite flexibly, I would say, issue queries against the state of the object, depending on how someone's decided to save it. I've implemented version control, so every time you save an object to the database, it just creates another version, another immutable snapshot, and you've got all your previous ones, just like Git. There's an identity map, which means that MinSpy knows which objects you have in memory, and if you pass an object to a function or something, it knows by that reference, okay, this is this object, which corresponds to that in the database. If you save it, it knows what you're saving, so you don't need to worry about there being duplicates or anything like that. There's an optimistic locking strategy, so if two of you save the same object, well, the first one to save saves normally, and the second one to save will receive an exception, because it'll say, well, the object's changed in the meantime, you need to update yourself. Metadata, that's super important. So you can, like all our databases, I guess, you can attach metadata to these things that just set aside from the object that can be queried in a completely transparent way. And there's a GUI as well, which is, again, key to adoption, because people aren't always that familiar with diving straight into database code. It can be quite overwhelming. So the GUI is super useful. It's also been great for discovery. We've also managed to make it work very well as part of people's daily workflows. Okay, and then on top of MinSpy, I created this thing called PyOS. Now, PyOS is a way of representing your database objects in a file system like structure. So you've got folders, and you've got, instead of files, you've got the actual objects themselves. So, why limit ourselves to these binary files? Why don't we have Python objects as the sort of central unit of things in our database, in our file system? Now, PyOS, you interact with it through an IPython shell, for example, or Jupyter. You've got familiar commands that I'll show you. You can pipe stuff, you can sort of find something, pipe it to another command, and so on. And you can have flags, ls -l like we used to, -r, and so on. And the key thing is, there's 3 active researchers in our group, and then several students. We're all connected to the same database. We've got things in common folders or disjoint folders. But, there's a root. We can always go and see what other people are up to or what's going on. And of course, it's all interactive because it's one central database. Okay, in the interest of time, let me move on to show you a quick demo of what this is all about. So, again, shout if this is too small or whatever. So here I have, let's say, my IPython shell, and you can see I've asked pwd, and I'm currently in this Optimate folder. What I have in there is some objects that I created for the demo, and you can see it tells me the type, just like a standard ls -l command, if you like, and then the name of the file, which is often just a UUID, but you can, of course, rename them to whatever you want. So to show you what you might do, let's, for example, create an atoms object, just a wire from their demo. So now I have this ASC atoms, and now I can just save that thing, and I get this UUID out. So, of course, I can ask, is this thing in there? So that was a standard ls, I can do it -l, and then add a -p, which prints something about the atoms, just so I have a quick idea of what's going on. And like I said, you can rename this thing, so nv is the rename, so I can make that, my wire, like this, and then I look back And indeed, I have my wire here alongside all of my other objects. And there's a little star here just to tell me that the database knows that this thing is currently live in memory and it knows about it. One other thing I can do to quickly find out what's inside objects is I can, for example, use the cat command, which of course, you know, can't just cat you the content. What it does is actually it loads up the object and calls the directory call on it to look at what are the attributes of that live Python object. And all I'm doing here is just representing it in a slightly nicer format, this kind of a box. So that's a quick way to find out what it's all about. And then I can move around objects on my virtual file system. So you can see here I have this directory called atoms where I've just been depositing some atoms objects. So I can move that one I just created into atoms, like so, and then I can go into that folder and find out what I have there. And you can see it's just a bunch of objects, which isn't so useful, but maybe I can do something like ls minus p on them. So I get an idea, okay, so there's mainly hydrogen molecules, some gold in there. And if I really want the details, then I can pipe all of that to a cat command, where it's just going to show me these boxes for all of them. Alongside that, I can do things like set metadata on these things. So, for example, these two objects, using their identifiers, I could say, okay, they're actually ground state structures, for example. That's my choice what I have to set. Let's set that metadata dictionary to be. And then I can quickly find all ground state structures, or ones that have that set on their metadata. So it says, okay, that's those two, and then I can, of course, cat those and have a look. Okay, so I have an object here that's an H2 molecule, and it has an ASE single point calculator attached to it, and an associated energy and forces because it was used as part of a calculation. So the reason I mention this metadata stuff is because we use this extensively to allow people to effectively rearrange their directories however they want. So if I go back up here where I was originally, which is the Optimate folder, I can just issue a find here, and by default find will go recursively down from the folder I'm in currently, as it would in Linux, and it finds those two things. So the directories are up to the user if you use the metadata in this way. You can quickly restructure and set up your project how you want. The final thing I want to show in the console is just an example where I might want to look at the history of something. So if I have a person object, so this is just a Python class I created called person. We can have a look at it. So I just create one. I have a name in there, and I have an age extra field. Fine. Now, save that. Can you hear me? It said something about on meeting by the host.
No, we can hear you.
Okay, great. Okay, so I have this person object, and now I can save it. Let's save, and it gives me my usual object ID. All good. And now I can mutate that object. So I go, okay, me.age, my birthday was last month, and I turned 35. So great. Now I've got two versions of that. Now I want to ask the historian, okay, can you tell me all the history of this object? There's two entries in the history, this one, and this thing here indicates the version number. Of course, the latest one is always the one you would normally deal with. The history is kind of like Git, it's hidden away from you most of the time. But if I really want to look at that history, I can go to the 0th entry and then look back at the age. And I see the age was 34. However, the current version is at 35. So there's these kind of hashed snapshots kept in time. And of course, you can prune these things and so on because your database can just explode if you're keeping around everything forever. So that's very, very quick overview of the command line. And then let me just quickly jump to the GUI. So this MincePy Explorer. So I just connect to my MongoDB database, and I can see, okay, I have all my objects here. For the moment, these are not split up into the folders. It's just showing me a flat view of everything, but that's in the works. And I can see the types that are in there. This one has no name because it was an anonymously created Python object, but I know it's the person. So you can see this is the state that was saved when that thing went into the database. and Indeed is there, and I can search for it and sort by it. Perhaps more interestingly for us is if I look at, say, a VASP run. So I run VASP, and I have all these VASP run objects, which are ones we created internally to store people's VASP runs. I can look for the ones that I've done, for example, like this one. And down here, I can see the actual current instance data of that Python object live because the GUI has loaded it. So there's a lot of stuff going on here, but really the only pertinent stuff for me is having a look at, okay, results, great. So I've got final results and energies and forces, so on. But on top of that, I've also got all of the steps from the optimization. So each step the optimizer did is saved, and I can look at that here in the atoms history. So you can see we have the different snapshots, and any of these snapshots you can call up. Say I want to view the atoms, and there's a plugin system that allows you to say what should happen on that right click, and we just call up ASC's standard visualizer. You can even say, actually, I want to see the whole atoms history as a trajectory. So that will pull up again, ASC's visualize, shows me what the energy did as I optimized. And then, of course, I can flip through the frames. The hydrogen molecule just moved a tiny bit, so not a lot happened. And then finally, I also store many of the input and output files. These are stored in alongside the database. I can call any of these up and view the raw file that I have. So again, this was really important. People were really asking me for this because people are really, really wedded to these input and output files, and I totally understand. So when we sit together, my colleagues would often ask, okay, I don't want to see these Python objects, give me the files. So we put in a quick way for them to just call it up and see what's there. Okay, so that's a quick rundown. Let me wrap it up and just maybe mention a little bit of what I think could be a link to Optimade. So the main thing, because I don't necessarily see us serving a huge amount of data, although that would be amazing, and I would be super open to that if we had things people are interested in. I mainly see this system using Optimade as a client. So the first step of a study, I'm studying metal air battery anodes. I want to download all of the structures with zinc and a few other things in them and just re-optimize them myself. So, a question to you guys, and I'm a little bit out of the Optimade loop, trying to catch up a bit. Is it possible to have a programmatic version of FDNA Skyscanner, right? Can I query one place that will aggregate all of the results from all the databases? That would be super cool, rather than having to loop over all of them. It's not a big difference, but I think it'd be nice to have. And then, of course, if we get to having enough data, I would love for this to become a server of Optimade stuff. But one thing that would be super useful is that, by way of motivation for me, is if there's a web interface that is standalone and can interact with an Optimade API, then I can just implement Optimade in MincePy, and automatically people can view structures using this standalone interface that I can just maybe launch as a Flask app or something. That would be super cool. So in a way, that's another question to you guys, and maybe it's obvious. Get out with it. Okay, so let me finish there and let you guys put in the comments questions if you have them.